In this tutorial, we will be discussing the VSEPR theory and the effect of lone pairs upon it. Just as a review, the VSEPR theory stands for valence shell, electron pair repulsion, meaning that the electrons are trying to get as far away from each other as possible. It's based on the number of electron groups attached to the center atom of the molecule. The arrangement of the atoms attached to the center atom minimizing the relative repulsion between the electron pairs. There are 5 basic geometric families: the linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And in this tutorial, we're going to be breaking these down and showing the effects of lone pairs on that center atom and how it affects its shape. So why do these distortions occur? Well, lone pairs require a lot more space, or a little more space, than an actual bond. The need for space causes a distortion in the bond angle between the atoms. The types of the atoms that are bonding to the center atom also create a distortion, and that's a result of the size of the atom. The bigger atoms take up a little more space. And then types of bonds between the bonding groups also make an effect, whether it's single, double, or triple. The molecular geometry, or the shape, will vary dependent on what kind of electrons are being repelled. The shape is a derivative of one of the basic shapes, one of the 5 groups. So if you look here, this is tetrahedral because there's 4 things coming off of it, CH4. If this H wasn't here and there was a lone pair here instead, that would cause a distortion, pushing the other ones down because the lone pair takes up more room. And then finally, if we have 2 sets of lone pairs, if it was water, once again, those take up more room, so it's going to cause even greater distortion, shrinking that angle even more. The placement of lone pairs around the center atom, you look at the geometry of the molecule. You want to minimize the electron repulsion and want to occupy a position within the structure that has a space for allowing everything to spread out as much as possible. Lone pair and non-bonding electron groups occupy more space than the center atom. The electron density is exclusively on the central atom, rather being shared between 2 atoms, like bonding electrons. This affects the bond angles, making them smaller than expected. The relative size of repulsion forces interactions are lone pair is the greatest, lone pair bonding is in the middle, and then bonding pairs are the smallest. So if these were all bonds, it would be 109.5. But because of that lone pair, these are bouncing off more than this and this. So the lone pair interaction is greater than the lone pair bonding interaction. So let's look at the tetrahedral geometry first. This happens when there's either 1 or 2 lone pairs surrounded on the center atom. All belong to the tetrahedral electron geometric group, but will have different molecular geometries or shapes. The first one is a pyramidal. It has 1 lone pair surrounding a pair on the center atom and 3 atom groups. And then we have V-shape. V-shape is if there's 2 lone pairs on the center atom and 2 bonding groups, when there are 4 electron groups around the center atom. Bond angle for the distortion were both less than 109.5, which is if there wasn't any. So here's water as an example for the V-shape or the bent shape. We have a bonding angle here, or a bonding pair there, a lone pair here, and a lone pair here. So what's happening is those lone pairs are bouncing off of each other more, pushing these two hydrogens closer together. And so instead of 109.5, it's 104.5. Let's move on to the trigonal bipyramidal. Alright, so the trigonal bipyramidal, originally we have the triangle in the center, and then the axial groups going up and down. The axial groups are 90 degrees, while the equatorial is 120. Well, because the 120 are more spread out, that is the one that's going to be replaced by the lone pair. The lone pair favors the equatorial because of the fact that those are more spread out. So if we look at the trigonal bipyramidal a little bit closer, this happens with 1, 2, or 3 lone pairs on the central atom. All belong to the trigonal bipyramidal electron geometric group, but will have different molecular geometries or shapes. The first one that we're going to discuss is the seesaw. It has one lone pair here that's not drawn in because it's not bonded to anything, but it's still taking up room, so it's pushing the other bonds out a little. And that turns into a seesaw shape. They call it this because if you turn it on its 90 degrees, suddenly you have a seesaw or a teeter-totter. A T-shape is when you have two sets of lone pairs. And you can see, once again, if you turn it on its side, how it turns into a shape of a T. And then when you have 3 lone pairs, it turns into a line, which is linear. So let's talk about octahedral now. This has 6 electron groups surrounding the central atom, indicating the octahedral electron geometry or the family. The distortions happen when one or more lone pairs occupy the 6 positions. Unlike the trigonal bipyramidal, all of these are 90 degrees. Since they're all the same degrees, there is no one place that the lone pair is more likely to go. So any one of these 6 areas a lone pair could be placed in. In distorted geometric structures, the bond angle between the axial and equatorial positions will be less than 90 degrees. So in the first one, we can replace one of the bond that was at the bottom. We're going to replace it with a lone pair, and suddenly you still have that square shape, and you still have a pyramid. It's just not 2 pyramids, one on the top and one on the bottom. And so you get the shape square pyramidal. So that's 5 things coming off of it with a lone pair. Square planar is if you have the 4 things coming off of it, and you have 2 lone pairs now, because it wants to be as far away from each other as possible. The lone pairs are going to be on opposite sides. So here's a summary of all the geometric shapes. So if we look at linear, that's our only option. But with trigonal planar, if one of these was replaced by a double bond or a lone pair, suddenly we have a bent formation. Tetrahedral, you have 4 things coming off of it. If one of these are replaced by a lone pair, you get a pyramid. If another one of these are replaced by a lone pair, you get a V shape or a bent shape. Now we have trigonal bipyramidal. If one of these was replaced, then you'd have the seesaw shape. If you had replaced another one, you get a T shape. And if you replace a third one, so this is 3 lone pairs, you get a linear. And then we have the octahedron. If one of these was replaced, you get the square pyramidal. If another one was replaced, you get the square planar. And that's an overview of the geometric families and how they break down and change when lone pairs are added to the central atom.